knew about it. So that was a fun exploit. Wrote up a QuickTime exploit for Tiger and Leopard, and this uses the execute payload from the heap stub. So it's a good example of how you can use that in a real live exploit. Also, the QuickTime Java to Qt pointer vulnerability. This is what I used to win the Pwn2Own contest in 2007, which is also another really great vulnerability. They let you just read and write arbitrary memory across the full address space from a Java applet. So once you have that, it's really game over. And the two payloads that I talked about, the staged bundle injection and the iSight photo capture. Okay, you have to forgive me because I'm going to have to make up some time with some of the more complex stuff. So the last section I'm going to talk about is local bundle injection. On Windows, the remote thread injection is a pretty common technique, which lets you load a DLL into a new process and inject a thread, and you can basically load a DLL and call functions in it. I had to write all this stuff in OS X by hand. And so to understand how this works, you have to know that OS X is this hybrid operating system that it uses parts of Mach and FreeBSD. And it's essentially the top half of FreeBSD ported to the bottom half of the Mach kernel. And what makes it really interesting is that there's a ton of different interfaces into the kernel because of the sort of dual ancestry of Mach and BSD. You have traditional BSD Unix system calls, which are executed with positive system call numbers. But if you use negative system call numbers, these become Mach system calls. And these send basically system calls directly to the Mach part of the kernel. There's also BSD sysctls and IOCTLs that you can use to communicate with it. But the Mach kernel primarily uses RPC to communicate. And so Mach is built with RPC messages to communicate between different processes that they call servers. This was the main idea of a microkernel-based operating system. And you would communicate even with the kernel through this same mechanism. And OS X still uses that for a lot of things under the hood. And this uses Mach IPC, which is built on what are called ports, which are these unidirectional message passing-based IPC mechanisms. And different processes have rights on, or different tasks have various rights on these ports. So you can have a send write on a port, which allows you to send messages to it. But only one task may have a receive write on a port, which essentially gives it ownership of it because it can receive those messages. But the entire security model of Mach is based on these rights. So for instance, if I receive send writes on the port for another task, that means I can send messages to the kernel about that task and read and write its memory, create threads, and do whatever I want to it. It gives me full ownership of it. And there have been a number of vulnerabilities in OS X that arise from the discrepancy between BSD processes and Mach tasks. So here's kind of a diagram of how they interact. A Mach task has the Mach threads in it, the list of Mach ports, and it also owns the virtual memory. The BSD process, which is what you're used to interacting with, kind of encapsulates all of this, in addition to the BSD-specific things like file descriptors and so on. And there's a way to map between the BSD process and a Mach task. These are the two system calls called task for PID and PID for task. Task for PID was very fun, has a very fun history as well. But also keep in mind that a Mach thread and a POSIX thread are very different. So if you can, we're going to create Mach threads in a remote process, which are supported by the Mach system calls. But once you call a library function in that thread, it's going to expect to use POSIX thread local storage, which doesn't exist, and it's going to crash. So here are kind of the system calls that we're going to use. We're going to create a task. We're going to create a thread in a new task, and then use the direct memory allocation to allocate memory in a different task, deallocate memory in a remote task, and then read and write memory from it as well. We're also going to use the secret sauce of Mach exceptions. These are how debuggers on OS X work and why GDB has to do a bunch of special stuff. Basically, on OS X, ptrace, the normal debugging interface that Unix systems use, is essentially broken. Doesn't really do anything because all this functionality is implemented using the mock, direct mock system calls that I talked about and mock exceptions. Unlike exceptions in like Windows, for instance, or Unix signals, you can actually handle these by a thread in another process. And so what you can do is you can attach to a thread or attach to a process and say, I'm going to handle exceptions for this thread or for this process. And so when there's an exception, it'll first get handled to the accepting thread's exception handler if it exists. And if it doesn't handle it, it'll send it to the task's exception handler. And if that exists, and if that doesn't handle it, it'll convert it into a Unix signal and send that to the BSD process. Really, really ugly, but it lets you do some cool things like the crash reporter on OS X is this global process that sets itself as the exception handler for every task. So if any process crashes, it gets a message saying, oh, this process crashed, and it can write the crash dump log to your file system. Or it'll pop up, most often you'll see it by it popping up a dialog saying this application has crashed, what do you want to do? And so to inject a mock thread, what we do is we gain access to a task's task port. So we use task for PID for this, or you can use a local attack to gain access through a vulnerability. And then you just allocate memory for the thread stack, and we have to paste in some code as a trampoline. And then we create the thread, assign the registers for that thread, so that it'll execute the trampoline using that stack segment that we've given it. And what this trampoline does is promotes a mock thread into a POSIX thread. And basically by reusing some functionality in the libraries, we can do this by just calling pthread set self and cthread set self. These will execute the system calls into the kernel to set the kind of magic registers, like the GS register and various other things, so that all the other thread function calls know what to do when they need to access thread local storage and things like that. And we can use this. Wait, did I talk about? Oh yeah. So and and so the way we're going to use this is we also need to use exception handling to catch our return values. So we can inject a thread that'll call a function, but we don't know when that function terminates or when or what the return value is. And so we'll just have that function return to a known bad address, and our exception handler in the injecting process will catch it and obtain the return value. And then we can basically use that to call remote functions at will in the remote process. And from there, we can do deal open, deal sim, deal close to load a bundle from disk and inject it into memory and do whatever we want. Or we can inject the contents of a bundle file directly into memory, just like we did for the exploit payload. Call ns create object file image from memory, ns link module. That'll link it up and send it going as well. And then once we have this injected, there's a variety of things we can do. We can hook functions and Objective-C methods to log SSL traffic from Safari, log chat messages from iChat, do any of these things. These are just what I've implemented so far. So the final remarks on our final ferocious cat. 64-bit processes are allowed on OS X, and these actually, ironically, make exploitation much more difficult. And because this allows them to break backwards compatibility and just do new things. For instance, page permissions are actually enforced, so that if it's not executable, you can execute it. All the addresses contain 2 null most significant bytes. This makes it really hard to hard code these addresses in because those 2 nulls will either truncate a wide character copy, or they'll also terminate an ASCII string copy. And while you can use the trick of an early termination of a string to kind of use like the string copy function to write out a null most significant byte, if there's 2 null most significant bytes, you can't use this trick. Also, very importantly, function arguments are passed in registers. You can no longer use the return chaining. And so basically, a lot of the techniques that have been built up for other operating systems just won't work on 64-bit processes. And as OS X starts using more 64-bit processes, even though they don't have a lot of these security defenses, this will make exploitation much more difficult. But at present, the very few security-sensitive processes on Leopard are actually 64-bit. The only one is Apache. For instance, your web browser, still 32-bit, still easily exploitable. Snow Leopard is the next release of OS X that's supposed to fix a lot of these things. They say it's a security and stability upgrade. And they say we're really not going to implement many new features. But are users going to pay for a new operating system with just security fixes? It's hard enough to get users to upgrade to more secure versions of operating systems, even if there's other features in it. So that's yet to be determined what they do and whether people will adopt it. In conclusion, OS X is vulnerable to the same types of malware attacks as Windows, even though we aren't seeing it yet. And because it's increasing market share, it is becoming at more risk for these attacks every day. And it doesn't have these exploit defenses that other operating systems have. But what makes it fun is if you haven't gotten into writing exploits yet because a lot of these features are making it a pain in the ass, well, just write them for OS X because you don't have these things to contend with. And so, writing exploits for Vista is really hard work. Writing exploits for Mac is fun. So that's all the time I have. I went over, and the thing tells me I don't have any time for questions, but I have a minute left. So if you have any questions, you can find me afterwards. Yeah. Okay. Thank you very much.
Thank you very much, Mr. DinoDaiZovi. Moving forward, we're going to cap off today's presentation in track 1 with Anthony Borowski and Jim Giovetti talking about Hacking the Bird in the Sky 2.0. Give us 5 to 10 minutes to set up, and we'll be right with you. Thank you.